Yakup benim 1992 doktora talebem. Yani onu sonradan devam etmek hakikaten bir emotional.
Kendisi Tennessee Üniversitesi'nde başladı polimer hayatına. Ondan sonra üniversitede beraber çalıştık. Arkasından 3 senedir Purdue Üniversitesi'nde çalışıyor. Uzmanlık alanı mühendislik lastiklerinin iç yapı özellik ilişkisi. Bu bağlamda da tam bizim konuştuğumuz konuların devamı olacak. Mükerrem Hoca'ya ayrıca teşekkür etmemiz lazım. Çünkü bugün ve dün aldığımız bütün eğitimlerin organizasyonu ve ne kadar biz yaptık gibi gözüküyorsa da kendisi bizler için burada ayarladı. Hem PAGEV hem de Türk sanayine birçok önde gelen hocanın gönüllü bir şekilde ders vermesini sağladı. Onun için ayrıca
teşekkür ederim. Sağ ol. Şimdi Yakup benden çok iyi bu polimeri Türkçe öğretme konusunda. Kusura bakmayın, ben bunu İngilizce size vereceğim çünkü teknik terimleri bilmiyorum Türkçesinin. Burada fazla şey vermediğim için. Size bir de bu konu belki yabancı gelebilir. Tavsiyem, anlamadığınız şeyleri beni durdurun. Yani rahat bir şekilde bu dersi yapalım. İstediğiniz soruyu istediğiniz zaman sorabilirsiniz, hiç çekinmeden. Önemli olan bir şeyler buradan kapabilmek, size bilhassa endüstride faydası olsun diye. Gördüğünüz gibi benim Türkçem o kadar süper iyi değil, onun için İngilizceye döneceğim biraz. Tercüman hanımlar da biraz scramble ediyorlar. Okay. Bizim yapısal polimer konusundaki terimler biraz yabancı olduğu için belki tercümede de zorlanmış olabilir. Eğer o durumlarda bir şey olursa o kelimeleri falan bana söyleyin, ben daha fazla izah ederim. En azından resimsel olarak. Şimdi İngilizce'ye de switch etmek Türkiye'de zor oluyor. The structure development and polymer processing is a complicated process. Now, what we are trying to do is to take long chain molecules. We design long chain molecules in various forms. That's where we start, chemical architecture. We either make them, Yakup has described it very well. Some of them are amorphous. They don't crystallize. And some of them are semi-crystalline. And they crystallize very fast, like polypropylene, polyethylene, because they are glass transition temperature. I just learned glass transition temperature, jumps the temperature. I just learned it. So I learned a lot in 10 minutes. So they are well below the room temperature, so they always crystallize. And there is a third category. So we really categorize the polymers from a processing point of view in 3 different categories. Polymers that never crystallize, polystyrene, ABS, polycarbonate. And there's polymers that sort of slowly crystallize, polyester, PET, PEEK, polyphenylene sulfide. And those are very rigid molecules. I'm going to review them again and again. And they're very flexible polymers, polyethylene, polypropylene, polyoxymethylene, and so on, that has TGs well below room temperature. Because of that, they always crystallize, and because they are simple molecules. So, we start with the chemical architecture. The chemists, that's their domain. So we literally do something to it, and Yakup described in great detail what really happens to them and how to take care of the problem, because semi-crystalline materials, they also undergo crystallization, and crystallization usually involves shrinkage. And then, so you have to take care of it. İşleme, I just learned the İşleme wording that you use. Very cool. So the processing essentially dominates how these materials converts into some sort of a structural hierarchy. Here's an example of hierarchy. This is an injection molded polypropylene, microtomed, and if you keep on zooming, and you eventually get to the polymer chain level, so that this is called hierarchy. So you really need to understand the whole hierarchy. This is a spherolytic structure. This is the shear-oriented layer. And here are the spherulites. And spherulites made up of lamellae. These are small crystals. And then this is basically unit cell of polyethylene, not polypropylene. So you have this hierarchy. And then if you truly want to understand how the process conditions, the injection speed, the mole temperature, the temperature of the melt influence the other properties, you really need to be able to characterize at these length scales. And you can certainly start with the optical microscope, but by the time you get here, this is a transmission electron microscope. And if you want to go this level, you need to do X-rays. So we use a range of techniques. Optical gives us a reasonably large size information. Every laboratory must have a microtome and an optical microscope at the minimum, just so that you can slice it, and especially if you have problems with the making mole parts, and then there are issues related to the warpage, shrinkage, and so on. And some of this directly points to the morphology that you have created by the process. So as a result, you must have at least this one. Even if you don't have AFM or TEM and X-rays, at least this. And then if you have an AFM and SEM, that's even better. And then go down to the X-ray gives you much more information. I'm going to give you examples of what kind of information you can get from these techniques. Okay? So you are in the business of making all kinds of plastics. You have an amorphous materials, and as I said, the crystalline materials, and each one of them are different. Amorphous materials, a lot of people prefer because they don't undergo shrinkage dramatically like the polyethylenes and polypropylenes do. So dimensional stability is much easier to control. But Jakub has showed you how to take care of even the shrinkage behavior. So the essence of it is that the molecular architecture, this is just 3 different kind of materials examples, how it dictates in the process. The flexible molecules like polyethylene and polypropylene, in the molten state, you have sort of a random percolated network with some entanglements and so on. And some polymers that have aromatic groups, polycarbonate, for example, they tend to have more rigid segments, or block copolymers that have rigid segments connected with the flexible segments. And there are those materials, I don't know whether they are common in Turkey, the thermotropic liquid crystals like Vectra and so on. It's not too much. Right. Those are really like a wood, matchsticks. They don't bend. They are literally like a matchsticks. They look something like this. And they behave very, very differently depending on what you do to them. So these are also, we're talking about all thermoplastics. And one of the most important things that you must remember in the case of polymers, compared to small molecules, polymers are never at equilibrium, This is an important concept, that no matter what you do, they will not go to their lowest energy state. They will always stay at some non-equilibrium state. And because of that, you have issues on the thermal residual stresses and density changes over time. Aging is an important issue. And so this is what we polymer engineers live with. We have to basically accept the fact that the material inherently changeable while it's sitting at room temperature or in an environment. So you have to do something about either quantifying an expectations or design your product so that these are taken into account for long-term applications. So that's why the microscopic structure is governed by the kinetics of what you do to it. So flexible chain molecules, we typically have a polymer chain. You might have some side groups. It doesn't matter what. It could be chlorine, for example, PVC, or whatever. And then if you have an irregular polymer chain, they usually are amorphous, atactic polystyrene. The glassy polystyrene, they call it. This is in this category. So that's pretty much it. But sometimes, even though it may be atactic and non-regular, if you have a small X, they actually can crystallize by slow cooling, or you can quench it into an amorphous state. Remember, this is all kinetics process. If you cool fast enough, These materials, they usually have glass transition temperature above room temperature. You can quench it into a glassy state, and they can be, in that state, metastable. They can just sit there until something happens to it. You heat it up, and it will just have enough energy to crystallize, or just simply a slow aging process. And some of you may have experienced, you make a part today and test it, and it looks great. A year from now, it changes. Because as it sits in the shelf, aging process takes place. Polymers densify. Their density changes, they shrink. They gradually densify. The free volume concept is an important concept to keep in mind. I don't know whether Jakub covered that, but that's very important. But it was in the PVT diagrams that he was talking about. The free volume is an important part to control. So if you have a regular chain, you can quench it into an amorphous state, and this is a dominant factor for making this. It's a polyester bottle. To make the polyester bottle, you injection mold a preform, right? It's a tube. Many of you, I don't know if any company makes these things in Turkey, in the crowd. And you make it literally amorphous because glass transition temperature of PET is 85 degrees centigrade, 80 degrees or so. So you take this injection mold it, and material is completely amorphous. And you heat it up to about 90 to 100 degrees centigrade, and you put about 450 psi. I don't know the metric conversion of it. Pretty high pressure. Then it literally explodes like the process behaves just like a rubber balloon that you blow up for your kids, literally like that. And we've taken a high-speed video of this process. So that is an important first step for doing something else to it. This is a classic example. It's a very classic example. And if you do a slow cooling, obviously these same materials that has a TG above room temperature can be made into a crystalline state. And then advantage of the semi-crystalline materials are, as we all know, that a number of properties enhance when you crystallize it. First of all, their operating temperatures goes up, so that you can actually use them in higher temperature applications. But at the same time, you can also get some additional benefits like chemical resistance and so on and so forth, because it's much more denser structure. The small molecules, oil, whatever, cannot penetrate into it. So those are the advantages of crystallizing it. But the penalty is it's much more difficult to do, and then Jakub described you how to handle it very nicely to maintain the dimensional integrity of the part. So the crystallization, as I said, just reviewing it, two really different processes, fast and then slow. And fast ones are the ones that have TGs below room temperature. Slow ones are the ones that usually have the above the room temperature. But there are other factors that influences stress. What you do to it during the solidification, or cooling rate. How fast are you cooling? And then a combination of these two also plays an important role. What happens to the crystallization of these? Chemical regularity, purity, and the flexibility, all of these part of this involvement. I'll talk about the secondary crystallization also. I encourage you to stop me if you have any questions. I'll try to answer in Turkish, but you know, my technical abilities are not that great. So going back to polymer chains, we are starting with the typical example of polymers are basically like a bowl of spaghetti, okay? It literally is like a bowl of spaghetti when you're talking about, I'm not trying to make you hungry, but closer to lunchtime. So they are basically our wiggly things, the bowl of spaghetti. When they crystallize, there was a lot of controversy. Let me give you a little history of morphology of polymers. Up until 1950s, they weren't sure exactly how the crystals formed. Many people thought that these sort of structures exist, and then nothing else matters. And so there are amorphous regions, and there are crystalline regions, and in between there are some disordered regions, and so on. They call them fringe micelle model. And fringe micelle model turns out not necessarily applied to everything, but it applies to some of these relatively semi-rigid materials like polyesters, these materials, that have difficulty basically folding. And this is the other model. They call it a chain folding model. Basically, this is called lamella, okay? And the crystal structure is part of the lamella. They just simply stack up. So a chain basically arrive and just simply folds back and forth, back and forth, back and forth. Once in a while it comes out, and so on. And these lamella sizes are on the order of 100 to 500. It's most of the materials. Somebody asked a question on polypropylene. Polypropylene is about 100 and 150 angstroms, 10 nanometers, 10, 15 nanometers or so. They are that thick. And you can, by process, without knowing, you actually control the size of this. And we'll talk briefly on what that is. So it's a chain folded model. As you can see, it's a much more regular. And once in a while, this is called cilia, literally like an animal cilia, sometimes biologists calls it. And so sometimes if you allow the material to crystallize without too much disturbance, then they call it a regular folding. So they go up and down and very nicely stack up together. But sometimes when you do fast cooling or some other kind of rapid solidification, this is called a switchboard. Remember the old telephone system? Switchboard? Literally like that. They just switch back and forth. But still, the key point of the polymer crystallization, just to take away from this slide, is that they have to become parallel. Polymers cannot crystallize when you're doing this. They have to become parallel. And this is an important one when you are doing a processing, where you're making fibers, films, bottles, injection molding. Processing is going to influence whether or not they're going to become parallel. Because if you do things that makes them anti-parallel or not prevent them from becoming parallel, you're basically preventing it from crystallizing, even though it has the ability to crystallize. That's the important takeaway from this. So if you take it extreme situation, that you go and take polyethylene, what is this? This is polyethylene, yeah. This is polyethylene, and you make it a 0.1%, very, very dilute solution at about 120 or 90 degrees in xylene. You can dissolve it. It's basically like a xylene liquid. So you almost know. What you're doing here in this case is that it's not a spaghetti ball anymore. Polymer chains all by themselves in a solution. They are not touching each other. There's no entanglements with each other. And they're just simply by itself. So if you very gradually cool from high temperature, this may take almost sometimes a week. This is not a process where you can make money, but at least you can make these entities. And you say, why are you doing this? Well, this is an important first step. Understand the intrinsic behavior of the material by just building these. These are called single crystals. And polymer single crystals, they are basically hollow pyramids. Thin. They're about 100 angstroms. If you put it on a solid surface, they collapse. They don't have any strength. That's why you have these wrinkles. You see these wrinkles? These are because they're flattened pyramid. And actually, in the solution, they're like that. It gives us an idea about what happens to the, if I eliminate all the possibilities of entanglements and no influence by neighboring chains, this is what the polymer will do. It will form these nice crystals. And very important thing is that the reason why they form pyramid, because you see these chain folds, these chain folds, they are basically a strain. That strain causes the material to shift up like this, so that it will avoid the straining, and that leads to these sort of pyramid structure. So the fold is actually a defect. Interior, more dense than the fold regions in the material. You can say, well, why should I care? Well, it does happen in the solid state too. And then when it does happen, it will translate into properties and other things. So it's better to start from the first structure first. The shape of these crystals are changeable. And we're going to talk about the crystallization. It all relates to various materials, polyoxymethylene, polyformethylene, Teflon, and so on. They have different shapes. It doesn't have to be just it could be flat ribbons. PET, for example, forms like these. It's all about how the polymer chains coming to a crystal. And interestingly, when the crystal is growing, it says, I want to grow in that direction because my energy for barrier is more favorable, and as a result, they become shaped. Have you ever watched the bugs walking on water? On the rivers, right? You know what the phenomenon is. The phenomenon is the surface tension. So that surface tension is holding the bugs. I just wanted you to remember the picture. Is the same thing that happens on the surface of a growing crystal. So there is, even though you're going into lower energy state by crystallizing material, in order to take the polymer chain to put it on the surface, it costs you energy because you have to push through that barrier to go into the water. So that barrier is the surface tension. And that surface tension, in the case of water, is isotropic. It doesn't matter which direction. But in the crystals, it depends on the direction. Some directions are easier to penetrate than the other directions. As a result, you make shaped crystals. And this is buried in your injection molded parts. You don't see it, but it's there. It actually, this is the basic building blocks of how the semi-crystalline material grows. Okay? I have to tell you, this 90 to 120 minutes that I'm going to tell you, it's a semester-long class. So, so that's why I was encouraging you to ask me the questions, because there's a lot of details that I'm not giving you. But I just wanted to give you at least some takeaway points for you to use, usable information. There's a lot of depth to it. I will have some equations. Don't be afraid. I'll skip them, and I'll give you more qualitative information on it. So if you go from more concentrated solution, now the polymer chains, they sort of know that the others exist inside a solution. There's more concentrated solution. They form structures like these. It's called a pre-spherulitic structure. What's the spherulite in Turkish? Sferul? Yeah, okay. What? Kürecik, okay. Anyway, so it starts with the ribbon. Typically, these are individual lamella, remember I told you? And then they form these structures. This is called a sheath. It's like a, best way to describe it is like, you know, when you buy a nice flowers to a lady, and then you squeeze it, that's just like that. So it spreads out, but on the center is bow. The sheath is called. So that's typically what happens. So they have they form and they branch and they branch and they branch and they branch, and you kind of see it in the electron microscope. This is basically taken out. This is when you get more dense. Here's an example. You see, it looks more like a squeezed flower, bouquet of flowers, and that literally like that. These are all these lamellar structures from various polymers. When you put the solution and with a simple stir, and you can actually do that in your laboratory, you just simply stir it, you will grow our famous shish kebabs. That's the Turkish contribution to the polymer science, shish kebab, literally. This is the shish, and this is the kebab. That's right. We're going through the whole menu. I am disturbing the lecture. I know. I'm making people hungry. Shish kebab is an interesting, and it recurs. And here you can actually see them isolated very nicely. You can see individual shish and kebabs. There's still issues about what happens in the case of the polymer growth. The shishes, they tend to have, I can use this, great. So typically polymer, when you have a polymer, you usually have a molecular, you don't have a single length polymers, you have a distribution. So typically polymer have sort of a bell-shaped molecular weight distribution. There are some very small short chains and very long chains. So this is a very important point. I'm not going to dwell too much into it, but the long chain molecules, these are very extremely long chain molecules. They also can entangle much more easily than short chains. Short chains are like they slip very easily, but long chain molecules, they are extremely powerful for polymer processing because long chain molecules can transmit forces to locally. If you apply stress, if you apply shear, they will penetrate into the local level, and you can influence the molecule behavior at the local level. And that's an important thing. So the premise is the shish part actually forms first. People haven't really completely seen it. And then the kebabs basically grow on the shishes. And kebabs, they look like a lamella, just chain-folded lamella, typically, that happens. And it happens because long chain molecules. So remember, and then many of you must be using polymer blends. And then sometimes you may want to do self-blending. In other words, same polymer, but different molecular weights. So if you want to small amount of increase at high molecular weight, you can dramatically affect the morphology development in the process. A lot of people got patents on it. But you have to be careful. There is also thermodynamic miscibility issues. Literally, the same material with different molecular weight can be phase separated. But it's a tool. Morphology gives us a tool to be able to design a blend that can directly be applicable to your injection molding process if you want to get them oriented, for example. All right. There are other ways of doing it, and I'm going to show you how to influence this. These are much nicer kebabs and shishes. You see that there's a shish structure, and kebabs, they have really grown as a result. And what you see the dots here is that they put a gold decoration for electron microscopy, so they become more visible. They're just simply gold particles. So as Jakub was saying, is the shrinkage is an important part. That when you take the material and then put it into the mold, and if you do a bad job of it, if you do a too deep quench into a cold, very cold mold, you may end up with a void. Literally, material basically breaks itself apart, and you've seen it. You say bubbles, what bubbles? And you think that it's because it's the moisture that came out. No, literally the materials rip itself apart as a result of that. Yeah, exactly. Injection molding. What material? Polypropylene. Wow. So there. And so at the minimum, at the maximum is this. At the minimum, it actually creates a density gradient. So you might have a density gradient on the skin. When you have a density gradient, the material is metastable, meaning that not stable. If it has an opportunity, it's going to change. If it's going to change, then your customer is going to say, well, the dimensions are no longer there, and so warped or something, and then it ties directly into the crystallization process. Important. So that's one of the things on the polymer crystallization. So quiescent melt. Quiescent, the word quiescent means undisturbed. You're not doing anything. You just simply take molten material and gradually cooling it down. And this is the kind of structure that you would get in a two-dimensional. So sort of a dendritic-like structure, okay? And then so this happens to be a blended polymer so that these dendritic structures are much more apparent. You can see the internal structures of these materials. So it's not uniform. So the crystallization process is not necessarily uniform. It's not what's called, let me repeat that, it's not volume filling. So if you watch it, and I'm going to show you a video. Okay. Let me go back. Some people, this is really remarkable. And in fact, this video that you just saw, I'm going to show you again, is the first time that anybody actually seen a lamella that is growing in AFM, atomic force microscopy. This is how it grows in the melt. This is a single lamella, like this. And people have seen this. we're living in times of amazing, and it always makes this sort of a curve because of all this strains on the two ends of the material. This is a real AFM study. As it happens in the crystallization process, they have seen it. At University of Bristol, they did this a long time ago. Amazing people. Not relatively new. So what happens is that the AFM, to continuing on the AFM observations, typically, this is, I think, for a rubber crystallized. It literally starts with a single lamella, as you saw, and look, and then they've taken a TEM pictures. Look what happens. It keeps turning into like a flower bouquet, right? It's always narrow in the center and keeps growing and so on, and eventually become a sphere. So even though you may end up with a spherulitic structure, you start with a rod. And then eventually, they call it a splay action. This action, this separation from the major growth is called splaying. And if you notice, there is a lot of empty spaces in between. Those empty spaces says that even though my crystal growth is here, I haven't converted everything to a crystal state. So if you're used to small molecule crystallization or ice freezing on your windshield, when there is a crystal growth, when there is an ice formation, that front, before this, everything is completed because it's small molecule. Polymers don't do that. Polymers actually, they say, I'm going to grow along these, let's say, two lamella. In between, still molten material. That molten material, it actually undergoes secondary transformations later on. They call it a secondary crystallization. This is very distinct. If you're coming from a small molecule world to a polymer world, it's completely different way of looking at these morphologies. So this is how graphically the spherulites, or so-called crystals, grow. Start with a rod and splaying action, and eventually sphere. I hope I'm not going too fast for the translator. Is it okay? I hate to drive the ladies crazy. All right. So the second important thing is, as I said, is that the polymer has a molecular weight distribution, and long chain molecules, what they do is they basically go in and out of many different lamella, like these. It's like a stitching process. Because of that stitching process, we have a significant advantage to ceramics and metals and all small molecules, because it gives us, this mechanism gives us the toughness. That toughness is a very important consideration as a result. So the same chain can go in and out of multiple. It's basically doing a stitching like you're making a three-dimensional fabric, literally. All right? Here's an electron microscope view of that sheath-like structure. You see the initial bouquet narrow portion is still visible, but outside is there. It's a beautiful picture. Somebody did that. Polyphore metal pentene 1. This is sort of a distant cousin of polypropylene. All right. Well, if you try to look at the AFM, now is a multiple lamella growing. This is also another amazing picture. Every time I look at it, I learn something. I want you to look at the growth. So the growth front is here, and it's going to grow this way. And I want you to look at, these are individual lamellas. Amazing how they visualize this. And see the black regions? They are amorphous. They are melt. They have not been converted. It will repeat several times. You see the empty spots there? So it's never volume filling. It's not, so this is how the crystallization occurs in your molds, in your injection molding process. That unconverted material actually gets converted later. They call secondary crystallization. So the part of the reason is that you have all these ribbons that are forming lamella. Those ribbons form, they basically shoot out, and they capture the molten unconverted material and then they can convert it later. So the shish kebab, they actually did that also. 2 shishes, one is here, and the other one is, and they actually saw how these shish kebabs are merging together. You see? They're all converging together, and then you have almost like an interdigitizing, so intermingling. İç-içe, right, that's the word. And then if you watch it, and you will see that sometimes they get avoided, the larger ones dominate, small ones die, and there's a lot of infighting going on. It's like a family fight. There's a lot of fighting because they are all fighting for the same thing, taking the molten material and crystallizing. And if one of them is dominating and the other one basically dies and then it becomes short, the other ones get longer and so on. There's a distribution of these. It's not as simple as this, as you can see here. So this is polyethylene crystallization in the backbone. Now, in the larger scale, so if you have a microscope with a hot stage, you can actually get the material to crystallize, and this is what you typically see. And I'm sure you have seen this, right? Look what happens. I'm going to stop the video, and we're going to talk about what happened. At distinct locations, nuclei, what did you call it? Çekirdek? That's so cool name. So nuclei in there, and there, they are formed. And this is quiescent. We're not doing anything. We're just simply cooling it, okay? Important observations. If you want to, I'm going to make you a morphologist. If you look at it, what do you see? You see a number of crystallites. You also see a size of the crystallites. What do you think about the size of the crystallites? They are about uniform, aren't they? What does it tell you? In time scale. It gives you lots of information. The reason why they're all the same size, because they started at the same time, which is an important point. They all started at the same time, right? If there was a size distribution, then, yeah, so see, this started later. That started later, that started later, but several of them started together. And some already sort of impinged and merged together. So in the early stages of crystallization, they are not aware of each other, right? Like here. They don't care. It doesn't exist. They simply don't, they just do what the thermodynamics tells them. They just simply grow. As you go forward, then they start becoming aware. Right there, they're coming closer together. And then as soon as they impinge, they can say, wait a minute, we're done on that point. And they impinge here, impinge there, impinge there. And then they form these interstices, and we're going to talk about this. And there are defects that you actually can literally create. This was a German video that I stole. I'm prolific theft about these educational materials. I just steal from anybody who can give me an idea to give. So the structure like this is nylon 6. So you have a spherulite with lamellar structures and entanglements, and then you have branch points and so on. So this is typically what happens. And size of the spherulites, they tend to be about microns to the several microns. All right, so I'm going to skip some of these. So the important thing about the spherulite morphology. Remember, the lamella is growing radially, right? Mostly radially, some splaying. But within the lamella, polymer chains are sideways. So when you look at the morphology, that the material's polymer chains are actually tangential to the growth direction. So 90 degrees, because of the fact that they're all folding and then just simply going up and down, up and down, up and down. So this is an important thing to keep in mind, especially if you're doing post-processing with this material. If you're doing cold rolling, for example. These details become important in the material's morphology behavior. Molecular weight chain length. Remember that the molecular weight distribution that I showed you on the graph here, that if you make the material fractionated, make it really long chain molecules, this lamellar structure gets less and less perfect. Look at that. There's high molecular weight, long chain molecules, they don't do very well in getting these perfections. So when you go to really high molecular weights, even though you have the same repeat unit, crystallizability or crystal structure integrity decreases for the long chain molecule. You have an ability to crystallize faster maybe because long chain molecules can entangle in the melt, but ultimately all these entanglements is going to be problematic in terms of quality of crystals. See, the short chains, they make a much better looking lamella than long chains. So keep that in mind. So when you're blending, when you're doing compounding, these are important issues to keep in mind. So to summarize, so high molecular weight materials can crystallize. They are capable of crystallizing, not necessarily, depending on the chemical architecture. This is the most important thing. Most people don't really appreciate this. They have to become parallel to crystallize. So when you do crystallize it, you have to have both the crystalline and non-crystalline domains, although they may have both same composition. Let me address the number 3 issue. Sometimes, excuse me, sorry. I forgot the microphone. So our chemist friends, they give us these molecules, right? It comes out of a reactor from petchem or whatever the reactors. When you look at the repeat unit, CH2, CH2, polyethylene, right? Or the polypropylene, CH2, CH, and CH3 on the side is polypropylene. Not always so, because there's always some side reactions. There's always some other groups that are sort of a defect along the polymer chain. So what that translates into this is that the local level is that if they don't fit very well, they either act as a defect in the crystal or they get excluded from the crystal into zones between the crystals where it will haunt you from a mechanical property perspective. It can deteriorate your material. All right, so. All right, I said that this is about stitching that I told you. And typically quiescent conditions, you always get spherulitic structure. And chains are always tangentially oriented. And now what I have shown you is what we call a thermal crystallization. We haven't talked about stress crystallization. Thermal crystallization involved polymer chain going to the interface, as you saw, and in order to get there, it has to diffuse through other chains and then grow. How many people are engineers here? Lots of engineers. Let's do some little thinking experiment. This is a very simple process. You have a surface that is growing, and polymer chain wants to go there because it's the lowest energy state. So how am I going to control this process? In between, I have a liquid. What's the phenomena I'm looking for? Viscosity, diffusion, related. So how do you control the viscosity? Temperature. What else? Pressure, yes. What else? Concentration, exactly. What else? Long chain molecule versus short chain. Huh? Volume. Yeah, that too. But short chains versus long chains. Long chains cannot diffuse as fast as long chains, short chains. Right? So short chains can diffuse faster under the same conditions than long chains. So you got it. So you know how to control all of this. So thermal crystallization is controlled by the viscosity that controls the diffusion. Molecularly, it also, well, it's not totally independent because if you reduce the molecular weight, viscosity goes down too. So you know that. So that's sort of related. Keep that in mind because that's going to come back to us when we start looking at the processing. of the material. How are we doing in time? 1 hour? Half an hour? I don't think I can finish in half an hour. But anyway, I'll do my best. Huh? Okay. All right, so the questions arises: kinetics of polymer crystallization, effect of process variables, temperature, pressure, and mechanical strain, effect of chain chemistry, blending, and the fillers. I'm going to talk about the fillers because I think industrially much more relevant. I'll give you some examples. What happens? Everybody talks about nano composites, right? Well, nano composites do influence the crystallization. I'll show you. So the question is this: what is the environment the polymer chains feel during their flow and solidification? It's a simple question. What do they feel? How many people have taken the rheology course from John Vlahopoulos yesterday? You've taken it, right? Polymers are viscoelastic, right? They have memory. They are sort of our grandparents. They remember the short memory, but they forget the long. Well, they do remember. My grandparents used to remember when they were a child too. But they have a short-term memory. And they're viscoelastic. That's why I say they have a viscous and elastic part of it, and then that actually influences the material's behavior. So what I'm trying to prepare your minds as to what should what conditions under which that I should consider to figure out how the material is going to behave in the process. Is it instantaneous conditions? Mold temperature, temperature of the melt inside the mold, or what has happened to it on the way to that point? Viscoelasticity says material has a memory, so what happens in the prehistory does influence the material. And this is the complexity in the flow-induced crystallization, okay? And it's still keeping us busy for a very long time. So they're non-isothermal. And the polymers, one of the most important properties of the polymers are their thermal conductivity is very poor. When you have a very poor thermal conductivity, the opening of the mold takes time. That's why Jakub told you can take out the nylon at 130. I can't believe it, actually. Really? Wow. 130 degrees. Well, it's still 100 degrees below the melting point, so it's perfectly OK for material. But 130 degrees, that's pretty hot. Yeah, you can burn your fingers. Temperature gradient. And as a result of that, because you have a low thermal conductivity, you have a sharp temperature gradients. That's a given. And sharp temperature gradients is important. And pressure, obviously, we have high viscosity, and pressure generation is relatively easy, and deformation is also, especially if you have a high molecular weight in the material. So let me go a little bit into thermodynamics. I hope I can carry you guys a little bit. Very simple concepts. And I want to give you some ideas so that we can build up to some understanding of how the materials behave. So free energy is a very simple concept. So the typical polymer chains in the liquid, they follow this kind of curve, a sharper curve, liquid. And this crystal has a more shallower kind of curve, and they at some point, this is the temperature axis, they meet at that point. So the difference between the crystal and the liquid free energy becomes 0. So we define that as a melting point, okay? And this happens to be a TM0, that's an equilibrium melting point. So essentially, an ideal situation that you never get in a polymer position. You don't measure this in DSC. This is hypothetically large, extremely large crystal, almost infinitely large crystal, that that will give you that maximum temperature. What is the melting point of polypropylene? 167? Wrong. That's not an equilibrium melting temperature. Equilibrium melting temperature of polypropylene is around 200 and something. What that tells you, you are at 167, but the real thing is 220. So the material is metastable. It wants to go there. If you give it time, if you provide sufficient thermal energy, it wants to go to that direction. That's what metastability is. That's one of the things that it's kinetically trapped. It's solidified and trapped, and 167 is for polyethylene. High-density polyethylene is 136, right? It's kinetically trapped. But if you look at the equilibrium melting temperature, it's much higher. All of the polymers that you measure is always much higher than what you normally measure on differential scanning calorimetry or whatever your melting technique may be. So about what this is, this curve is very important. About the equilibrium melting temperature, you have to really work hard. You have to put energy into the material to keep it solid. You have to go up, right? Because the liquid has the lower energy state. So the system wants to go down that way. It's much easier for it. It doesn't cost you energy. And below the equilibrium melting temperature, it's the crystal, opposite. The liquid wants to go to a crystal state. So difference between the two is your driving force, thermodynamic driving force. You're closer to the equilibrium temperature, the smaller that driving force gets. The larger the difference, the bigger the driving force. Very simple, thermodynamically. So material really wants to go into crystal state when you are over here. If it is closer to here, it says, OK, I'm going to mosey along and get there much more readily. OK? So we deal with the nucleation process, checker deck formation, right? And the growth. Literally, you form, and then you also have a growth process happens. So the typical classical theory of nucleation deals with large atomic arrangements in a very small volume. What that means is that you have a crystal, and then you have a whole bunch of spaghettis, and then one of them says, I'm going to go there and start forming. Very large organization, and it starts folding. Magically, this folded structure form. OK? So in the process, you have, this is just a demonstration of what the condensation is. I want to remind you of the bug. This is a very important concept. The surface of the crystal is that, just like that, what the bug is feeling. The material wants to go jump in, but there's a barrier. The barrier is the surface tension. Right? So this is not scary equations, but let me explain. So we have a crystal, a spherical growth crystal. We just assume it's spherical growth, and the radius is r, OK? And it just simply gradually grows. So we have a volume contribution to the free energy. This is the volume contribution. So volume is basically says when you crystallize from a liquid, and we saw in the curve, it's negative. We are below the equilibrium melting temperature, so this is always negative. The surface contribution is always positive. So they fight with each other. So when the size is very tiny, when the size, this is the R, is very tiny, OK? The situation is like this. You're basically trying to climb up the energy scale. So it works, you have to work hard because surface dominates the volume because the volume is not much at that point. The surface dominates. Because surface is positive, it costs you. It costs you energy to climb up. But at some critical point, we call it the critical nuclei size, then everything balances out. Volume and the surface, they are balanced. After that, it's basically going to Uludağ and skiing down energetically. Right? You just simply go down because now the volume dominates and the surface doesn't. So you can quickly take a derivative of this. You just assume it's a spherical. It's very simple. This is the area. Assume it's just simply a circle, right? This is the surface tension. Take the derivative, and then when it's equal to 0, that's the peak point. That's your critical nuclei size. Very simple arithmetic. Anybody can see it. The reason why you have a negative, because this has a negative value because of the negative nature of how we measure it. Simple as that. So at the equilibrium melting temperature, the free energy is equal to 0. This is the classical thermodynamic equation. At the equilibrium parameters, entropy is enthalpy divided by the equilibrium melting temperature. You plug all that in. This is a very powerful equation for critical nuclei size. And this is where the thermodynamic connects to injection molding shop, okay? That size, that equation. Where does it connect? It connects with this. Critical size and delta T. This doesn't change much. This doesn't change, surface tension doesn't change. What really is connecting is the critical size to supercooling, meaning how far away from your equilibrium temperature. Delta T, this is delta T. Okay? What does it tell you? The larger the delta T, the smaller the critical nuclei size. How do you predict the morphology? You can predict the morphology now. Now you know this equation. You can predict the morphology. If I have a large temperature difference, I will have lots of nuclei sizes. That means my injection molded part is going to have so many small crystals. If my delta T is small, I have fewer critical sizes because because this is your barrier, energy barrier. If you cannot get there, then you just simply cannot go over it, and then all the nuclei that are smaller than this, they're going to die. They're not going to grow because surface dominates. So this is a very important effect, how the processing condition influences the morphology. Very simple connection. Very simple and very powerful connection. Where we use this is in the BOPP. Anybody is doing BOPP? I know there are some BOPP people in Turkey. So in order to make a polypropylene, to make a very transparent, well, that's what you use. You use this. Or nucleating agents, both. Çekirdek ajanları, is that what they call it? That's funny. Anyway. I'm learning a lot today, as much as you do, I guess. All right. Çiğdem, oh, that's cute. That's even cuter. So anyway, you got this, the idea. I'll just skip to that. So the critical size and this energy curve understanding and how it connects to the delta T is very important. This is one. So the crystal growth happens in the quiescent conditions. So we understand how the material's morphology evolves in quiescent conditions by just controlling the viscosity and the temperature. So the growth occurs if you draw a line in a spherotic. So they typically go to a relatively high density, and there's always, just to give you an idea of what happens in the neighborhood of the crystals, and there is a concentration gradient. So because the polymer chains are attaching themselves to the crystal, there is a little bit of a concentration gradient near the crystals. And this gives you the sort of a downhill effect on the diffusion process. So it gives you an ability to grow the material. All right, so what happens when you apply temperature gradient? When you suddenly change the boundary and cool it down, but no flow. We're coming to injection molding. So this is the case where still there's no flow, and I change the wall temperature suddenly from melt to some low temperature. I just dropped it. So above the melt, this is the energy curve. It just keeps on going up. There's no way you're going to go back down because there's no critical nuclei size. You will never crystallize above the equilibrium melting temperature, period. So there is a very nice guy named Andy Lavenger, a long time ago, 1978. He did this very simple experiment. He made a very thin film of various materials, nylons, onto a glass slide and put basically hot wire, just very simple hot wire. So you basically have this temperature gradient. And he just pulled it at a very small speed, 3.5 micrometers per minute. So you have a hot, and then underneath the wire, cold before, cold after, and he created these kind of structures. So what happens is that the same effect that we told you earlier also is at play here, is that when the material is contacting a cold surface, delta T, cold surface, right at the cold surface, your critical nuclei psi dramatically goes down. Because the critical nuclei size dramatically goes down, so you have so many of them. Okay? But if I have a surface here that is cold, but inside the molten material that's still hot, and our material says, I'm not going to give up my heat so easily because my thermal conductivity is poor, right? So I have a temperature gradient. So what happens? You have a whole bunch of nuclei formed. The only way, and they sort of, they can grow to relative to each other quickly, and then they bump into each other, or they're done. The only option that they have is going inside. So this is called directional crystallization. So the materials start crystallizing inside, and you create these kind of structures. This is very common. This is very common in injection molding, especially fast crystallizing materials. You can actually see that, and I'll show you some examples of it. It's a classic a microscopic observation without any effect of flow. Flow doesn't have anything here. Just simply, you heat it up and you cool it down really fast, and then this is what happens. Right? Here's other materials. Very similar behavior. Well, lots of details. Some of them grow alpha, beta for nylon and so on. I'm not going to talk about that. Here's an interesting experiment. In this particular Genesis Kriegel, this is from Austria. He do a two-step process. One is just quench it into a low temperature, and then he did a second quench to an even lower temperature. You see the difference in the second temperature, that the material's nuclei sizes are so small that the size were relatively big, but now in the second case, the material have a whole bunch of them, and then morphology changed immediately. You can do this. You can do the post-processing. In some cases, people do eject the molded parts while the interior may be molten. You can do that. You can control the inner morphology by selective temperature changes, temperature jump, jumping into a different environment, water, oil, and so on. These are all within your ability, as long as you know what the mechanism, morphological development mechanism is. You have the ability to do it. All right. So there's a primary crystallization, just to summarize, which is basically these lamella that are growing, and secondary crystallization, they basically filling off these between later. And these two are sometimes overlapping. Both of them might be happening simultaneously, and so on. All right. It's a cool AFM video. It's really worthwhile watching it because you can learn a lot by just repeatedly watching these. There's a lot of mechanistic details in here. If you watch it with a trained eye, it's very useful. All right. So the questions that's remaining, how do the nuclei grow? What processes determine the rate of growth? Right. So there are two different nucleation, and Jakub addressed to it. One is homogeneous nucleation. That almost never happens in practical, unless you do an extreme purification of a polymer. Homogeneous nucleation is basically there's no foreign matter inside the polymer, nothing except the polymer, and then it crystallizes by itself. And all of you know, in the best case scenario, the reactors will leave catalyst inside. They don't take all the catalyst out. Even the catalyst will act as a checker deck, was it? No. What? Çiğdem, sorry, that's even better. I'm going to remember that. So cute. At the minimum. So What you're dealing with industrially across the board is a heterogeneous nucleation. You either keep it as is or you enhance it. By enhancing and by just simply adding, there's a whole range of, there's a whole industry of organic versus inorganic nucleating agents, which I'm not going to cover. That's well established and in industry. What basically you're doing there is, energetically, let me explain, is you have a surface of a particle, very small particle. Instead of, remember that it has to start somewhere. The biggest problem of crystallization is that initial energy, right, that's costing you. If you provide a ready surface, well, the polymer will apply. I say, okay, took all that energy requirement away, I'm going to attach myself to it, if the energetics are right. So the biggest advantage of the nucleating agents is that you control the morphology much more accurately. So you know by concentration, you know what size of crystals that you can actually control. You can make it transparent by making them really small crystals. You can make them non-transparent if you make them, and so on. So it gives you an additional tool to control the morphology. All right. This is actually, somebody did the simulation of, and I also stole it. Simulation of crystallization. Just watch it just for fun of a polymer chains. This literally is actually the real dynamics of polymer chains. You see the crystallization occurring? They're going through the densification process. They're all becoming parallel. Unless they become parallel, they don't crystallize. But look at the dynamics. Pretty fast, isn't it? So they basically go through the this number of nuclei that changes. And the easiest way to do is just simply recording on the video. If you have a microscope in your laboratory with a hot stage, you can study it very easily. You make a very thin film, put it in a microscope, heat it up, and you can actually do it. I'm going to talk briefly about Rami Kinetics, which is a very traditional kinetics theory to give you some tools so that you can actually quantify the kinetics of crystallization. Actually, it wasn't the Rami. The Rami is an American guy who published in 39 and 41, but it's actually the Russian mathematician Kolmogorov. Russians are really angry about that. Even though it's known as an Rami, Russians said, no, it's ours. Kolmogorov. So they both said, and this wasn't, they weren't thinking about polymers. They were talking about metal alloys or something. So the one phase growing inside, beta phase growing inside, alpha phase growing inside the beta phase. Their assumption is that the growth is spherical, and then so on and so forth. So they basically assume that the nuclei form randomly, and so whenever the temperature is below the equilibrium melting temperature. So this is their expression of the nucleation rate, number of nuclei per volume, and how it changes with time. So it's all about this nucleation rate and how it controls it. So typically what happens is that if you're watching on the microscope, these crystals become, as you saw in the video, at some point you start seeing it, but in fact, they form much earlier. You can't see it in optical microscope. They're just too small, right? And then so time equals 0, the nuclei forms, and they eventually, so they are independent of each other, and they sort of impinge on together. And typically linear growth, and that's one of the assumptions that they typically use, linear growth rate. So when it's a linear growth rate, that's relatively simple. But this is the growth rate. You can just simply determine the size of it at a given time from tau to whenever the time is. And it's relatively simple integration of it, and you can get that. And if your crystal is a volume, you have basically a sphere, you can get the spherical information, you can plug all that in, and so on. So at the end, I just don't want to bore you with all these things. You can assume the constant growth rate and the nucleation rate is constant. So this is the how you determine the radius of a given crystal, relatively simple. Plug it into this expression, And what you get is a very powerful kinetics equation. This is called crystallization kinetics. Rate constant. It's an exponential term. I want to give you 2 points on this relationship. One is the nucleation rate, and the other one is the growth rate. And I want to connect it to something practical for you to take away. Growth rate, we already discussed. Remember the what controls the chain attachment to the growing? We discussed it. What was it? Molecular weight, viscosity, temperature, pressure, all of that. So these are the parameters that you can use to control the growth rate. And look at the equation. It's the third power, cube. So if you can control, if you slightly control the growth rate, you can control any of these parameters that controls the growth rate. You can directly influence the kinetics of crystallization, right? And this is the nucleation rate, number of nuclei, right? You can add a heterogeneous nuclei and so on. But it's the first power. What do we do industrially? We never control the growth rate. We control the nucleation rate. It's not that easy to do even though it's significantly powerful. But you can easily see, since the molecular weight controls the viscosity controls the growth rate, you can easily see what happens when you change the molecular weight. You go to a low molecular weight material, what's going to happen to the rate constant? Crystallization growth dramatically increases. So if you want to crystallize the material inside a mold faster, that's another tool. Lower the molecular weight. Lower molecular weight, faster diffusion, faster crystallized completion, faster ejection. If you can afford the reduction in mechanical properties. Everything is compromised, right? You want to go high production rate, or you want to go high strength materials, or what is it? So what you do is you optimize. High enough molecular weight, but not too much. Because higher molecular weight means it's going to slow down your crystallization process. All right. So the expression for the crystallization rate is given generically like this. This is 1 minus exponential k, the growth rate, and this is the growth type. This tells you about the dimensionality of the crystal. If it's three-dimensional, it usually is large, like a sphere. If it is needle-like, it tends to be like 1. So it goes from 1 to 4 or 5 or so in industry. You can actually calculate them. I'll show you some examples. For example, you can do dilatometry, very simple experiment that you can just simply jump the temperature to above the melting point and keep it there about 15 minutes and cool it to the crystallization temperature and watch the height of the liquid change. And from this, you can actually get the density changes. And you can just take a natural log of the log. That's very simple expression. And versus time, and plot that, and the slope gives you the n, and intercept gives you the k. And it's a very standard. In fact, if you buy any differential scanning calorimetry, nowadays software comes with it. You can actually do this on a differential scanning calorimetry, which gives you the crystallization profile. You just simply do a partial integration and get the same equation, and so on. This is fairly well established in industry. If you have a differential scanning calorimetry, if you're not doing it for your processing applications, you're not using your DSC. It's very powerful because these kinetic parameters is influenced by a whole bunch of things. As I said, the nucleation. Sometimes you get products that are unknown. So at the minimum, for your sanity as to how the material behave, I would do this. Relatively simple experiments. What's powerful is, and this is demonstrated here, is that if you change a little bit of growth rate, the crystallization rate dramatically changes compared to the nucleation rate. Even though we know this, we still try to play with the nucleation rate by putting nucleating agents. Growth rate is not so easily controllable because you don't want to sacrifice the molecular weight. So you just simply try to nucleate as many crystals as possible so that they all start at the same time, and then you convert them into a final solid product. All right. So kind of numbers are here. One-dimensional is 2, the end, and two-dimensional is 3, three-dimensional is 4, and sheaf-like is 6, and there's a whole bunch of, there are other regions that I'm not covering. Heterogeneous also changes. You just simply measure these, and then there are tables that you can get from nice books like Menderken's Crystallization of Polymers that you can follow. Typical N changes. This is a theoretical curves. So the gradual changes given you with 1, and much sharper changes is N is equal to 6 from the crystallization kinetics curve for the Rami equation. All right, some experimental observations, typical numbers that has been reported. Here is an Rami exponent, polyethylene, polypropylene. These are the ranges that people have. Nylons, so anywhere from 2 to 6. This is the space that is covered from the experiments. All right. One important thing is molecular weight dependency. As I said, when the molecular weight is less than about 10,000, this is typically for, I think this is for polyethylene. As N is 4, that tends to be more sheaf-like structures, okay? And then it's from 10,000 to about 1 million. It's about 3, that's you get the spherolytic structure. And when you go over 3 million, that's ultra-high molecular weight. Then the thing becomes so irregular that you no longer see spherulites. So the crystallization is basically sort of a hodgepodge of lamella, just random organization. You don't necessarily get this, because so high density of entanglements that you end up with an irregular structure. Ultra-high molecular weight polyethylene is great material, fantastic material. It's cut resistant. The reason why it's cut resistant because it has such a high density of entanglements. It doesn't cut. That's why I don't know whether it's in the Turkish market. The gloves for butchers, cut resistant. They use those. It's ideal material. But you cannot use it for super high performance systems. For high temperature applications. At the end of the day, it's polyethylene. It's going to melt at 140 or something centigrade. So it's not an engineering material. But they still use it for, you know, armor suits and things like that. So secondary crystallization, I want to revisit again. So I want to make sure that it registers with you when the crystal grows, inside that volume is not completely converted. It converts later. And you see that this is even the sort of exaggerated example of dendritic structure. All the black regions you see in between is unconverted, and it converts later. So this is a very important understanding of the material. Even though you measure the growth rate, well, it's only growth rate of some partially converted crystal structure, not fully. Keep that in mind. The polymers are different. All right. Now, what happens during the secondary crystallization is that people have studied it. They call it an insertion mode, and I'll show you. Secondary crystallization, so this is 100 degrees plus cooling to room temperature. And this is isothermal at 100 degrees for a long time. You can see the contrast between the two. This has more uniform lamella. This has more varied distribution of lamella sizes. So people have done this. What they found is that at some temperature, at high temperatures, and this is how you control the size of the lamella. Remember that we talked about it? So at high temperatures, you have this large lamella that is growing because material wants to grow at large thicknesses. So if you go to One step, you go to a lower temperature, right? Goes down. And this in between, the pre-existing ones, you get the thinner one. Because the crystal sizes become smaller as you go to a lower temperature. And we've already established that. So you go to a lower temperature further, crystal sizes gets even smaller. So you have a distribution of lamella sizes as you do essentially three-step. In this case, it's a three-step process. If you do it continuously, like in a normal injection molding, right? Skin cools faster than the core, you have a distribution of cooling rates, you're going to have this kind of a morphology. Some are thicker at high temperature. Where is it going to be? In the interior, where the cooling rates are lower. At the skin, they are thinner, and it's going to be at, so it's a different morphology from a crystal size point of view. So in reality, when you have a cooling, this is the kind of thing that you get, lamella growth. So T2, T0, T1, and T2. But in the normal situation, it's basically tapered. It's a tapered, sort of a gradually tapered. It's like a, so if you think about it, it's like a disk. So remember the shish kebab structure? At the beginning, it's a high temperature, and kebabs tips tend to get smaller. So it's not really like the usual kebab, and kebab with a taper. Okay, so that's the important message. The other one is very practical, this one. Most people don't appreciate this, but it does occur. When the crystals are growing and they impinge on each other, what happens at the interface where the material is not completely solidified, but it is confined by the neighboring crystals? And this is a very important phenomenon that most people don't appreciate because it leads to cavitation. The reason is, remember, when we convert it, this is a high density, this is high density, this is high density, this is low density. So once all that material is confined and depleted, you basically rip the structure apart. You create a bubble. You actually create a void. Okay? It's because that portion is actually under negative pressure, and you can see in equations and so on, but I'm not going to bother with that. So this is actually what happens. Here is the crystallization of isotac. This is polypropylene. So they are approaching each other. You see the bubbles? They form and they form and they form. And as soon as that negative pressure occurs, people actually measure the growth rate. It actually drops down dramatically because you no longer have the material to feed the hungry crystallization process. But look at it. What kind of property is going to be influenced by this? Impact? Yeah. Yeah. Excellent question. I suppose when you have a smaller spheroid sizes also, the confinement may not be as bad. It's much more homogeneously. So you may not see these probably. Look at the size of the spherulites in this case, 200 micrometers. You don't see that in industry. I think this is an exaggeration because they're almost like a homogeneous nucleation. Almost all of the polypropylenes are sold with the nucleating agents. People don't see it. They may not see it in the normal conditions because you have such a large amount of crystals that you don't see it. But it may still be there if you look for it. This is an exaggerated experiment. I just wanted to put it out there just for people to see it. These are gigantic crystals, 200 microns. It's huge, the crystals. So it always helps to have a homogeneous evolution of structure. That's why polymers, classically speaking, there is a correlation between brittleness and spherulite size. The smaller the spherulite size, the tougher the material gets. The larger the spherulite size, the more brittle the semi-crystalline material gets, always. Is all because of the fact, at the minimum, even if you don't have bubbles between the spherulites, the growth phenomenon This is well known in chemical engineering, where they use crystallization to purify the material, okay? They basically squeeze out all the foreign material to the interface. Well, in this case, and squeezing out is all the defective material. And if you have a defective materials basically surrounding the spherulites, your impact strength is going to suffer, right? So again, reducing the size of the crystals homogenizes the material and then lessens the issue. It's always there, but it's always, it lessens the issue. So one of the ways we actually look at, how are we doing in time? I have not come to the injection molding yet, so we are building up to it. I'm sorry. But as you can see, unless I explain all of these, we cannot talk about injection molding because it's just, you have to have the basics to cover it. What? All right, so here's a typical, what we call the C-shaped continuous cooling diagrams. This curve, this is the equilibrium melting temperature, remember we talked about? And Tg is somewhere below here. And this is the curve. This curve indicates, basically says, if I am at this temperature, it takes this long to create fixed number of nuclei in the material. So when you're closer to the equilibrium melting temperature, it takes much longer because driving force is less, the critical size for nuclei to form are larger, and then you get fewer of them. And as a result, it gets longer. As you go to lower temperatures, it increases. When you go approach the glass transition temperature, the opposite takes place because your viscosity dominates below here. So it goes down. So this is C-shaped. So we actually use this to explain the non-isothermal crystallization. So, okay. So material starts at the melt. This is the cooling. And if it, during the process of any kind of process, casting or fiber spinning, injection molding, if it encounters this curve, it actually says, well, I have sufficient conditions for crystallization to take place. And you have an energy release because crystallization is exothermic. And then you cool down. But if you cool, like on the skin, very fast, then the material basically ignores all of this and goes below the glass transition temperature, and this leads to a vitrification. Material become amorphous. That's it. It has no chance of crystallizing. So if you do a slower cooling, the nice thing about these kind of diagrams, it will tell you, excuse me, it will tell you at what temperature it's going to start crystallizing. If I do a slower cooling, it's going to crystallize at higher temperatures. If I have a faster cooling, it's going to crystallize at lower temperatures. If I go even faster, it will bypass this, and it will never crystallize. This is the portrait. This is the important understanding of non-isothermal crystallization. What happens when you add a stress to it? These curves change. When you add a stress, this is quiescent, no flow, and here's the flow effect. It dramatically shifts all of this curve to a high and low, and also shifts to a shorter time. So imagine this is the material that's quiescent, and right, it crystallizes. And this is the condition that it doesn't crystallize. So when you apply the stress, first of all, this material, instead of crystallizing at lower temperature, it actually crystallizes at higher temperature. This is the number one effect on crystallization. Okay? So number one, when you apply stress, like injection molding or fiber spinning, it doesn't matter which process it is, that it will always crystallize at higher temperature. That's number one. Okay? So the other thing is, those conditions that normally does not crystallize will actually crystallize. So the stress effect has a very dramatic dominant effect on the crystallization behavior. So this portrait always works on any process that applies a stress, whether it's a fiber spinning, injection molding, blow molding, injection molding. It doesn't matter, but conceptually it's the same. All right, so the pressure effect, I'm going to skip all this. Classical aperion is well known in chemical engineers, but I'm going to say hydrostatic pressure basically increases both glass and equilibrium melting temperature. So the pressure does dominate. Somebody here said pressure. Yeah, that's exactly right. melting temperature actually shifts up. Glass transition temperature shifts up. What that means is that when you apply pressure, suddenly the material says, I'm shivering because now I have a bigger temperature jump, and it crystallizes. So that's very important. So it increases the equilibrium melting temperature, right? And reduces the free volume. This is the volume between the polymer chains. So it squeezes it, obviously, you can imagine that. And also increases the viscosity. Now, that is bad from a crystallization point of view. So if you increase the pressure, you're helping the crystallization on one hand, but you're also increasing the pressure. You may nucleate faster, but the growth process is going to slow down. Which one is it? I'm confused, is the answer, right? That's what happens. That literally is what happens in the case. So this is the pressure effects on shear flow and then elongation of flow. It always goes up. And this is the expression that typically use, Arrhenius type. And temperature dependency of viscosity, those of you who've taken from John's course, is very similar to that. This is a Barros equation, just simply pressure dependency on the viscosity. Relatively simple. All right, so it's even more complicated. So this happens to be cis polyisoprene. This is one of those lower melting materials. It's a rubber crystallizable. What's interesting here is this. This is the, remember the Rami Kinetics? This is the Rami constant that had the U and an I. So if you are at low temperatures, look what happens. The higher the pressure, the lower the crystallization kinetics. At higher temperatures, opposite. Because at lower temperatures, remember the viscosity is so dramatically affected by the pressure. It dramatically slows down the crystallization because the viscosity dominates. But at higher temperatures, it's the other effect. The melting point increases, the material thinks that it is at the lower temperature and crystallizes faster. Complex situation, isn't it? So it depends on where you are. Opposite effect. In between, so I have a neutral territory. That's why you get these kind of growth rate behavior on crystallization at different pressures. This is 0.1 bar. This is 0.5 bar. You see that the crystallization actually shifts to higher temperatures, but the growth rates get smaller because of the pressure. So the two dominant effects. One is nucleation is faster, but the growth is slower. That's what happens in injection molding, right? In the initial stage, you have a fast packing, and then you have a packing stage, you have a dramatic increase in pressure. So where that packing stage influences the structure? In the interior, not on the skins, in the interior. Skin's already done by the time you get to packing stage. Skin is already solidified. All right, we're slowly getting into injection molding now. All right? Anyway, you can do non-isothermal kinetics. I'm going to skip that because we don't have time, so I'm going to go to the injection molding process. So, Jakub, I guess you showed you this, right? Yeah. So basically, in injection molding, I just want to quickly review it from my perspective. So when you inject a melt into a cold surface, right, what happens? This is the rectangular, it's the simplest cavity you can injection mold. You basically have a shear flow, right? But at the surface, you are well below the solidification temperature or crystallization temperature. And the material enters into it. What happens is that you have a dramatic change in geometry, flow geometry, because the red region is basically solidification front that is approaching both sides. And when they do, it also influences the local flow field, right? Here we have a gentle shear, but here it's a pretty sharp shearing flow. And this is called the fountain flow. And basically that the yellow skin regions, most people don't appreciate it, those yellow skin regions are formed of the material that has undergone biaxial stretching. This is literally, you're blowing like a rubber balloon. It's a biaxial stretching. Most people think that injection molding is all about shear flow. Not so. What do you call transition from here to here? It's an acceleration flow. What does that mean from conceptually? You're stretching it. You have not only shear, but there is an elongation component to it, right? So it is much more complicated than what the people say. It's all shear flow. It's a shear crystallization, shear this and shear that. Not so. It is, there is always an element of elongation in the formation of the injection molded part. The reason why I want to say this, which flow is most dominant? Remember, let's go back to the two ways of crystallizing the material. What was it? For crystallization to take place, polymer chains has to come together in parallel. They become oriented. Flow can do that. Flow can orient the polymer chains. Which flow is most effective to orient the polymer chains? Let me ask you this. You took, some of you taken the John's class, right? What do we have? Shear flow? Shear flow or elongational flow? Which one is most effective? Right? In the shear flow, the polymer chains are like random, and they get, what happens to it? They rotate and extend. So shear flow, yes, absolutely right. Elongation is much better because here you're wasting energy by rotating. Rotation has no effect on orientation, so-called vorticity. No orientation, only the elongation in the shear that helps you stretch the polymer chains. Elongation, so which process is the best? Fibers, right? That's why fibers get really highly oriented. So you have to consider what type of flow that influences the orientation because it's all about getting the polymer chains to become parallel to each other, right? So here is an elongation, and here is also biaxial elongation in this case. And then there's also a lot of shearing going on near the solid-liquid boundary, right? That's the solid-liquid boundary, and here's the shearing flow, and here's the biaxial extension flow. It's more complicated than this. So the best way to do it, what they call a Lagrangian thinking. Lagrangian thinking is like you are a fisherman, and you get into the river, and you're going along the river, right? And you're feeling the flow field inside the river as you go with your boat. That's called Lagrangian sense. So if you do that with a single point, you jump into let's say, jump into a hopper and go through it before it gets to the mold temperature. It goes series of, actually temperature goes up, it melts, pressurizes, and cools down, and then the temperature does all kinds of weird things. One of the important things about the polymers is that they remember what happened to them. They remember what happened to them. All of this history must be taken into account, especially if you can't figure out what is going on in your product. Not just simply what happens at the local level, not the mold temperature, not the melt temperature there, but what happened to it. What kind of a screw design, what kind of a shearing that I'm implying, what kind of a mixing elements that I have. All of these have a direct contribution to the material's behavior. I guess many of you are injection molding, have done injection molding. Have you ever seen a part that actually particle that has gone through injection molding process without melting? I have. You have too, right? So our material is so poor conductors, sometimes particles go through the whole machine without melting. Such a dramatic observation. Most people think that, oh, everything is homogeneous and so on. Not so. That's another consideration that we're not even touching, is that is this melt that is coming in, is it homogeneous? Is the temperature uniform within the melt itself? Assumption, if you assume it is homogeneous, you're wrong most of the time, especially on big machines. Usually there is a temperature distribution, and as a result, they actually put mixers, melt mixers on the machine, right? Tell me, you guys, you're in the injection molding business, just to homogenize even the pure material without any blends. All right. Let's go over some of the things. I went through that. Okay. I'll show you some examples of structure. Okay? Now, in this case, remember the thermal crystallization of polypropylene and so on? I'm going to turn off the thermal crystallization. No thermal crystallization, no diffusion. I just want to talk about orientation. And nice thing about these kind of materials, slowly crystallizing materials, PPS, basically you can turn off the thermal crystallization entirely. And you can actually look at it. Here's the injection molded part of polyphenylene sulfide. Okay? And it's injected at 1.5 cc's per second at mole temperature of 20 degrees, the TG of 85, and melting point of 280. So it's pretty dramatic difference in temperature, right? So when you look at the from skin to core, near the gate, pretty substantial skin, and there's a dark region and there's a core region that are transparent. Skin and core is transparent. And here, narrow portion has the thickest dark region, and then it disappears towards the end. Differential scattering calorimetry tells us that this one is basically amorphous, essentially. All the other ones, the maximum crystallinity is observed at some depth from the skin right here, about 60%. Skin is amorphous and core is amorphous. How can that be? We already said polymers are poor conductors. If the polymer is poor conductors, the inside must crystallize, right? If it's a polypropylene, it will crystallize. But these materials, the thermal crystallization is turned off. Because it's turned off, then you have an interesting effect of shear effect. All right. So what we have is an amorphous skin, amorphous core, and shear crystallized intermediate layer. And it's all coming from just stretching the polymer chains. Okay? This is the effect. This is the mole temperature. And same condition. This is the number 3 location on a very simple dog bone shape that were microtomed and then laid down in a microscope. So the flow is coming towards you. Skin amorphous, the dark region is crystalline, and core is amorphous. Look what happens when I increase the injection speed. That region disappears. Counterintuitive. The higher the injection speed, well, and we do influence the shear layer formation. If I go to a higher temperatures, it gets darker and darker. And remember, the TG is here, glass transition temperature. Above that, essentially material becomes homogeneous, dark. Dark means it's crystallized because size of the, yeah. Not completely, but to a certain extent. Yeah, yeah. But the bright means it's amorphous. So from a heat transfer point of view, if it was a thermal crystallization, this one, the center portion, should experience the slowest cooling rates. It should crystallize the most, but it doesn't. It's a dramatically different mechanism. So that's, I'm just trying to tell you the difference between thermal crystallization we've been looking at versus shear crystallization. I'm going to bring back both of them together, but before we do that, I want you to see just pure oriented, not necessarily shear, but oriented crystallization. This is oriented crystallization up to about this point. Beyond that, it gets complicated because thermal crystallization kicks in. Because you are above the glass transition temperatures, then here things are happening even if you're not doing any flow. So the contrast, this table, I just created it because I wanted people to really understand the difference between thermal crystallization with the traditional thermal crystallization and orientation-induced crystallization. So first requirement, chains need to become parallel to each other. Thermal crystallization, yes, by chain folding and diffusion. And orientation-induced, yes, by chain orientation, flow, and deformation. So both cases, they do it, but different way. In the case of it requires diffusion of polymer chains to growing front, the answer is yes, no, not necessarily. Because you don't need to diffuse anymore because you're orienting them locally. They don't need to come from far away. You're orienting them. So you don't necessarily have to have a diffusion. So if you have it, yeah, it's going to help. If you don't have it, it will do just fine. And as you saw there, because in the core of that previous observation, right, there's plenty of time for diffusion, but it doesn't. It doesn't crystallize because thermal crystallization is turned off. Right. For crystal perfection in 3D, there is a sufficient mobility in the change as crystallization occurs from mobile phase, solution or melt. This is traditional thermal crystallization. Orientation induced, we need to provide additional mobility for change to three-dimensional registration. I'm going to talk about this in a little bit. So effect of high viscosity, longer chains, lower temperatures, reduces the crystal growth. Diffusion is affected, right? We know that diffusion is affected. But if I increase the viscosity, it helps the orientation. So the high molecular weight material are more dramatically influenced by the orientation. Low molecular weight materials more dramatically influenced by thermal effects. So opposite behavior. So if you want to thermally, yeah.
At 1 o'clock, some people have to leave their rooms. So
Oh.
Asking for permission.
Of course. I don't know where I am, but I have to talk about Jakub's PhD thesis before I let you go. This is Jakub's PhD thesis.
We can continue after lunch. If you wish, just what time you need to go to your meeting?
1:30 is executive committee. Or the hotel people might be kind to allow them.
I extended it to 1 o'clock because now I gave my key to my friend.
Oh.
He's checking out.
Oh, I see. It's up to you guys. What do you want to do?
No, I think we can finish and we should go on. Somebody need to go.
Okay.
They can go and come.
All right. This is Jakub's PhD thesis. He worked on injection molding of polyethylene naphthalate. One of the best dissertations ever in my. I had about 65 students. This is one of the best ones. I'm not saying that he's sitting here, but it's really true. This is an injection. This is what happens when you have too much of an orientation. The polyethylene naphthalate has these naphthalene groups that are so easily orientable in the shear zones, okay, in this case. So dramatic is that you see that when Jakub did the impact testing, look at this. They literally exploded where those shear crystallized regions were. So too much, especially when you have a molecule that have a very poor interchain forces because of the naphthalene nature, it's almost like a mica. Then they literally explode. So shear crystallization may not necessarily work so well for your application. Well, I don't know. I can go through the modeling aspects of it, but I'm going to skip the modeling. People probably are not interested. They have since people are in a hurry, I'll skip all this. But essentially what we did was very simply, what I told you, the effect of the stress on this continuous cooling diagram is put into an equation that connects the stress to the movement of this curve. And secondarily, the rate constant is also controlled by the stress. That's also put into a functional form, as well as the Rami exponent. They put it together into a model. Just verbally, simply, we actually did the simulation, and this is the work Shung and Jakub also worked on this one, is that you can actually simulate this structure. So very similar simulations, the crystallinity evolution through the thickness direction in these materials. And if you go to higher and higher temperatures, then thermal crystallization kicks in, especially here. And then you have an interior now has a high crystallinity. Skin still has a lower crystallinity. This is experimental. This is simulation work. All right. So it's one-to-one correlation of what I showed you here is that we were able to simulate all of that very well. So what I want to move to a polypropylene, fast crystallizing material. Now, in this case, you have both thermal crystallization also stress crystallization. And I wanted to show you thermal crystallization separately and stress crystallization separately. Now we're combining the two because both of them happening in polypropylene. Here's how we do microtome, slice it, and take a picture. Here, in this case, we, in the center of it, took a picture. And this is the full microtome images of polypropylene. What do you see? Very similar to PPS. You have this fair amount of crystals near the skin, and you got this dark region, and you have the whole bunch of bright things spherulite. Let me show you close up. You see, this is the skin. This very skin is basically the yellow portion that formed by the biaxial stretching right there. And in between, interestingly, your nucleation rate goes down. So even though it's close to the skin, your size of the crystals are a little bit larger. And then you have this red region is this representing this dark. You see? What's interesting is that if you look on the edges, it's not necessarily homogeneous. There are some like threads are forming. It's like a shish kebabs and so on. Those are formations. This is on the edge. So in this particular case, obviously, when you have a shear domination, the extensional component domination, the size of the crystals becomes so small, this is what you get. Well, if you don't believe me, we actually did an X-ray diffraction. This is highly iron. We still haven't published this yet, believe it or not. So you have an X-ray, skin all the way to the core. You see that in the dark regions, the X-ray, you don't need to know what the X-rays are. Just know that there's a difference in sharpness. These sharpness indicates polymer chains are oriented this way. When the sharpness disappears, that means that's less oriented. That's typical of a spherulitic structure. If you watch it carefully, what you see is that these are small crystals. These are large crystals. Following the thermal crystallization, what did we say? Closer to skin, you have a faster cooling. Here is a slower cooling. Slower cooling means larger crystals. Faster cooling means smaller crystals. You see the gradient. That's typical for polypropylene and all similar materials, polyethylene, polypropylene, polyoxymethylene, and so on, and PVDF. All of them will exhibit one form or another this kind of a structure. Now, what I want to show you is more dramatic effect of nano composites. How many people work on nano composites? Yeah. Nanoclay, right? Nanoclay. Nanoclay in nylon is classic because that was the first thing that people have done. So nylon, when you injection mold a nylon, and here's the morphology for skin to core, it doesn't show a very dramatic shear oriented layer. Reason is nylons have very low viscosity, right? If they are polycondensates, they are very low viscosity. So all you do is a thermal crystallization, except maybe near the skin. If you look at it, it's a spherulite just frozen in space. And you have a larger crystals and smaller crystals closer to the skin. So no matter what you do, nylons do not orient because you don't have this mechanism of shearing because viscosity is so low that the material just simply doesn't shear very well. You cannot transmit forces to local polymer chains. It's classic. Here's a typical nylon, unfilled. Take a picture, homogeneous, uniform, and you don't see anything interesting. Injection molded, this was 50 degrees. It's cover up here. It's 130 degrees. It's funny that you mentioned 130 degrees, 0.8 inches per second. And when you do an X-ray diffraction, and you don't need to be a specialist to figure out what's what. When you do an X-ray diffraction, it's kind of boring. There's not much orientation. A little bit of orientation near the skin, but that's about it. And then it's not really a perfect crystal. It's just the rest of it is just simply unoriented, random. It's almost like a bowl of spaghetti. So you put in clay. This is what happens. Dramatic difference, not only on the skin, but all of the layers, all the way down to the core. Clay, and if you do an electron microscopy, clays are basically everywhere, dramatically. The clay structure, what's dominant in the clay structure is that they are very large plates, and very thin layers. So when you separate and disperse it inside the polymer melt, you're providing a solid surface against polymer chains that are low viscosity. Now imagine this. You have a solid surface and molten material that's next to a solid surface. What the polymer behavior is going to be? You're basically taking away the degree of freedom from the melt. You are dramatically changing the way the polymer melt behaves. But the end result is that you can literally orient full structure, not even the skin, but the rest of it, in the presence of the clay. Now this was mold temperature of 50 degrees. So we are creating a pretty reasonably large solid skin during the injection process. We also we said, okay, well, what if we go to 130 degrees mold temperature, pretty high temperature for nylon, just 100 degrees below the melting point, you see the same thing. So it doesn't matter. So you can actually get the orientation dramatically by just simply adding they call it a magical dust in there. Many people use nanocomposites for like a barrier applications and so on. I think the nanocomposites, what's the hidden value is processing aids. It will make nylons orient dramatically. And then the properties, obviously, relative to it would be dramatically influenced. That's not possible any other way.
Would you expect the same behavior when nanoplates are polyethylene?
Polyethylene has a difficulty dispersing the clays. But if you functionalize it,
It distributes well, but not dispersed in 10 years.
are you able to get exfoliation?
I think we couldn't characterize that.
I see. Well, TEM should give you that.
But we work with blown film. It's not injection mold.
You want to do the clay in polyethylene. Why do you want to do clay in polyethylene? Polyethylene is already for barrier. I see.
That's why you said immediately jumped into it.
Yes, yes. I actually
Regarding water vapor transmission rates, values get worse.
get worse,
Yeah,
not better.
not better. 10 to 15%.
I think you're creating defects.
Yeah, we made a breathable.
Yeah, you create exactly. So use that. You can probably make a sports apparel with that, breathable films. Yeah, because I think the clays, they are 1 or 2 micron in plane. So you can generate, if it's 1 or 2 micron plane, and if your film thickness is 1 or 2 microns, they are about the same dimensions. So you will create defects. Inevitable. But injection molded parts, that doesn't happen. Thick. So it's okay. The only other option you have is that you start with the clays that are very small in plane dimensions. They do have synthetic clays. If you use the synthetic clays that are in plane dimensions are smaller, you might have a better chance of getting, less defects in the material. What's your film thickness that you ended up with?
100 microns, the film thickness.
Yeah.
But we put them in the core layer, which was 45 to 50. It was a coextrusion
Uh-huh.
process, and the core layer was 50 microns.
Even then you get defects?
Yeah. But the mechanical properties did not alter. The elongation at rupture didn't change.
But water vapor transmission went up.
Yeah, but I must play with process parameters. For instance, for inner low layer temperature and the external temperature can be dropped, maybe can influence.
Absolutely. I guess you went away from EVOH because cost.
And it requires 5 layers. If I
Yeah.
do this,
I know. You wanted to make it a cheaper EVOH layer system. Yeah, I gotcha. All right. Well, you can't win them all. I think that's why I never mentioned barrier, because I'm not a fan of it. I think it was too much of a hype. I think it's more, I think the clay has a value on processing aid. Viscosity modifier, exactly. Especially for nylon, all the nylon categories should benefit from this. Polyolefins, they don't like it. I mean, you need to modify them. You need to put some sort of either chemically modify it to make the clay, but they never like it at the end of the day.
We also tried polyamide 6 at the core layer. So now I'm thinking of adding some nanocell with polyamide
Yeah.
at the core layer
Yeah.
to improve the oxygen transmission rate perhaps, because water vapor will be achieved by means of polyamide. But now I'm curious what I can get oxygen transmission rate performance.
I see. Okay. But the nylons are not so good with the polyethylenes. Adhesion problem. What? Yeah. So you need to get some sort of copolymers and so on. I'm almost there. So it's a shear amplification. What happens in this process that materials in between, they are so close to each other, you amplify the shearing, and then the two things happen. When the polymer chains close to the solid surface, their mobility goes down. Because their mobility goes down, plus you have a shearing, and then they dramatically orient. Because the mobility goes down, they don't disorient. That's the key. Even though the nylons have short chains. Polycondensate is all short chains, 40,000 molecular weight, no more. So the dramatic shear amplification occurs in the shearing action. So Barış Yalçın did that for his PhD thesis. It was also one of the nice work. Yeah. Not 3M. He's in Coca-Cola now. Yeah. Yeah. So the liquid crystalline polymers, I guess, not so relevant. Shall I skip that? Yeah. Rigid. So liquid crystalline polymers are rigid chains. So when you orient them, and no, I'll skip this since people are having a time. Just talk about the glass fibers. I guess lots of people doing glass fibers. So the important thing is that in the case of glass fibers, how does the flow influence the orientation behavior of the glass? If you have a converging flow, right? The converging flow, the glass fiber tends to orient in the flow direction. If there's a divergent flow, they do go transverse to it. So we've done a long time ago some studies on these. So the kind of flow type that the glass fibers undergo in a mold and how complex it is, and whether or not you have a converging and divergence and acceleration will make a difference in their orientation behavior. Here's the how we did it. Basically took a piece of microtome, and this is, you just simply put an X-ray source. This is a radiography that composite people use. But this is an ultra-high density glass plate, photographic plate. So you can literally examine this under microscope and see individual fibers. Okay, so that's what we did. So if you look at close-up, what you see is that dramatically this is an extensional flow, right? You see that this is, remember that biaxial flow? That the skin layer actually has lots of oriented that way and also pointing towards you. So they are, in the skin is not all in the flow direction. What's in the flow direction, this is the flow direction, is this shear layer that we've been looking at. These glass fibers also have a dramatic shear orientation effect. And then, in the interior, you basically have a parabolic profile that's frozen in the process. There are things that can happen in the this typical parabolic profile. It's following this profile. Potential delamination, especially in mechanical testing, was possibility right here on the shear, just like what Jakub saw in the PN. And dramatically in the core, we have seen these with depletion zones in the material. So the glass fiber can act as a bridge that can lead to this kind of a defect in the material. Blends, in the case of blends, especially when they are not miscible, like a nylon and polyethylene, skin, you will have all these fibers, and the core will be dominated by the spherical dispersed phase. So this is a typical behavior in the case of miscible. This is 70% polyethylene and 30% nylon. And in this case, a nylon is a disperse phase, and nylon is orienting inside the, near the skin. That's pretty much it. So one has to really understand the materials, what kind of material you're dealing with, and how it interacts with the processing behavior. I think that's pretty much it. I gave some references. Thank you. I'm sorry, this should have been a whole semester long course. You got an extremely dense version of a course. So if you do have any questions, send me an email. I'm in the internet. I'll be happy to answer you.
Hocam, PAGEV öğretmene teşekkür etmek istiyorum.
Öyle mi peki?
Öğrencimizle birlikte edelim. Şöyle alalım, bir de hatıra fotoğrafımız. Olur. Çok teşekkür ederiz katkılarınızdan dolayı. Güzel eğitim için. Kendimizi podyumda hissettik.
Hakikaten ha, valla.